Hi, I'm Sam Roberts from Roberts Geospatial Engineering. Today we're going to look at how to integrate sea level change into a terrain and bathymetry raster. So I had a question from a viewer on YouTube saying how can they integrate a variable sea level change into a terrain and bathymetry raster using ProRaster. And specifically, they wanted to know if they could use ProRaster Essential to do that. The answer is you will need ProRaster Scientific, but you can certainly do it. So we're going to take a look at how that can be done. ProRaster comes in 3 tiers: ProRaster Essential, ProRaster Premium, and ProRaster Scientific. You can acquire this software from the Microsoft Store, and you can download a 7-day free trial to give it a go. So here's ProRaster Scientific on the store. Today we're only going to use one data set, and that is the GEBCO Global Terrain and Bathymetry dataset for the Earth. Now you can get this from robertsgeospatial.com.au. Go to the data page, scroll down a bit, and you'll find GEBCO 2025, and there's a download link where you can download that 6.6 gigabyte raster, which is in an MRR format, and that's the one that I'll be using today. So firstly, let's look at ways that you can shift sea level up and down as a bulk shift without any variability in the shift. And you can do this in any tier of ProRaster. So I'm going to create a new algorithm for the GEBCO raster. Going to go into the color page and change to the Atlas color table, and that ships with the product, so you'll be able to make this straight out of the box. So we have terrain here in greens and yellows and browns, and everything from light blue through to dark blue is all below sea level. So that's our GEBCO dataset. So the way to modify GEBCO data on the fly to move sea level up and down is to use a data conditioning filter. So on your color page, you go to the component section and select the data conditioning filter. And here I've got one called change sea level. Turn it on, and you can see that there's immediately a change. So for example, Australia has now turned into an archipelago. So I've raised the sea level by some certain amount, and the result is instant, and you can see it on screen. So let's just take a look at that data conditioning filter. Here's the data conditioning filter editor. So I can just create a new one, and I'll go through that process. So add a new filter, give it a name, and I'll say lower sea level 300 meters. Hit the tick, and then come down here and turn on this transformation. So I'm going to apply a scaling and an offset. My scale will be 1. I'm not going to apply any scaling, but I'm going to put in an offset of 300 meters. Now I want to lower sea level, so that means I actually want to add 300 meters to my terrain. So I'll hit that. Then I'll go and select that data conditioning filter, and you can see the result straight away on screen. So we've lowered sea level by 300 meters. Australia is now a lot bigger. There's a whole new continent here in Asia, and so forth. Here's the UK. Doggerland is back. The North Sea is back above sea level, and so it goes on. That's how you can easily raise and lower sea level in ProRaster Essential, Premium, and Scientific. There is one other way to do it, and that is to go into your color table editor. Go to, for example, your system color maps, and here's the Atlas color table that we're using. You can clone that color table and then go in and edit it through this color table editor and change the position of the change the data map. So change the data values that the colors correspond to, and in doing that, you can move the sea level up and down. That's a fairly difficult way to go about it. I don't recommend doing it that way. In ProRaster Scientific, we have other options and better options. So let's turn this data conditioning off again. In ProRaster Scientific, we can go into the raster calculator. So let's take GEBCO, and I'm just going to use that one field, one band, and then we'll write an expression. So I want to lower the sea level by 300 meters. So I'm going to add 300 onto GEBCO. So A00, which is my code for the GEBCO input, plus 300 meters. I just need to provide an output file name. So we'll just call this GEBCO plus 300. Hit OK. And here's my raster. So let's go into the color page again, choose that Atlas color table, and you can see that we have now lowered the sea level by 300 meters. And once again, we have a new continent in Asia, and we have Doggerland back. Furthermore, if you come and look at the values in here, if I put in my tooltip key data value, you can see that the transition to sea level, to the blue colors representing below sea level, is at 0 meters. So what we did there was we created a virtual raster. Of course, the GEBCO dataset is a large dataset, but we didn't do any processing. We created a virtual raster, and when I display that virtual raster, it does everything on the fly at the resolution at which I'm looking at the raster on the screen. So there's no actual processing required to be done as a processing exercise. So that also provides us with a mechanism to change the sea level by a varying amount. So we would go into the raster calculator. I must remember that I have the webcam on. Go into the raster calculator, add in your terrain and bathymetry raster, and then you would add another raster. So select one raster that you've created, for example, and that would come in as another alias in this list. And then you would add those two rasters together, or subtract the two rasters, one from the other, depending on what you want to do. And that's going to add that. So if your second raster represents sea level change, then that's going to add a variable difference to the GEBCO dataset. Now, the good thing about the calculator is that there doesn't have to be any kind of equivalence between the rasters that you put into it. So your rasters don't have to have the same cell size. Cells don't need to be aligned. They don't even have to have the same projection or anything like that. The raster calculator figures all of that out. It does all the interpolation that needs to be done, and smooth interpolation. And so you can take like a low resolution sea level change raster or grid, apply that to a high-resolution terrain and bathymetry raster, and the calculator will do all the hard work for you. It will do all the interpolation and give you smooth interpolation of that calculator operation. So one way that you might do that is to do some gridding. So we're going to produce a grid from just a few data points that's going to represent sea level change. So I have here a CSV file, comma delimited. I just created this in a spreadsheet. So I've got longitude, latitude, and sea level change. And I only have like 45 values. Every 45 degrees from minus 180 longitude to 180 degrees longitude, and from minus 90, the South Pole, to the North Pole. So we have a very small little data set. And we're going to grid that data set. So I'm going to go into point processing and import multi-banded points. Now, this was designed to import billions of points, not a few dozen points. So you do have to be a little bit more careful about how you design your grid. So I'm just going to browse to my sea level change CSV file. Then I need to set up my columns. Now, as this is a CSV file, it picks up that header line and sets it all up for you automatically. In this case, it's even worked out that longitude and latitude are your X and Y channels. And so the only thing that I need to do here is specify that they are in latitude, longitude coordinate system. That's okay. Choose my MRP file for output. We'll call this sea level change. Again, I do need to specify the coordinate system. My vertical units are in meters. And now I'm just going to set the cell size. In this case, I've only got a few data points. I really only want one tile in my whole MRP file. So I'm going to use a cell size that will cover from minus 180 degrees to positive 180 degrees. So, and knowing that a tile in an MRP file is always 256 by 256 cells. So if I use a cell size of 2, that's going to give me full coverage. And I can also design the position of my tiles. Normally you would not do this, but in this case, I want the tile to sit squarely over the top of my points so that when I render my points, they appear in the middle of the screen. So I'll just hit that, import them. Here's my points. We'll just take a quick look at them. We're going to modulate color by sea level, change the size. So there's our points. So we have a 200 meter sea level at the North Pole. Here at the South Pole, we have a 300 meter sea level. And then you can see that there's some high points and some low points in between. Okay, so now let's grid this small point data set. So I go into virtual gridding. Again, virtual gridding was designed to work with billions and billions or even trillions of points. And this is not the application for virtual gridding, but it does work and you can use it. So let's give it a go. So I'm going to choose my MRP file, which is my sea level change, my points. There's my output MVR file. So I'm going to clip to a rectangle because I just want to, because otherwise I'm going to generate data that's outside of the range of data that I'm interested in, which is, you know, between the poles and 180 to 180. So I'll give it a bit of slack, 190 to 190 and 100 to minus 100 on the poles. I'm going to use minimum curvature because I want to generate a smooth grid. I'm going to turn off my convergence. I'm just going to let it do 50 iterations so we get a relatively smooth grid. I'm only going to need a tiny tile size. It's selected sea level for me. I'm going to put in a cell size. So you always have to design your cell size appropriately when you're doing minimum curvature. We've got data points at 45 degrees, so a cell size of sort of 10 degrees is appropriate. In this case, I'm going to use 5 degrees. So we're going to get a data point every 5 degrees. And then I'm going to adjust my resolution. So we're at base level at the appropriate resolution. And then the tile origin. So our tiles are 256. In fact, what we could do to make the math simple, if we put in 4 degrees as a cell size, we know our tiles are 256. So if we center it on 0, 0, that means we need we're going to go from minus 512 to 512 degrees. So we can put in a manual tile origin of minus 512 degrees and minus 512. So again, we're going to be centered on our data set. The tiles are going to be way outside of it, but that doesn't matter because we're clipping to this smaller area. So that's okay. Let's hit OK. Okay, so there's our grid. Let's just see it as color. Perhaps turn on some contours. So just select that grid. 5-meter contours. So here's what we're looking at. So we have a smooth raster. We're at 300 meters sea level change at the South Pole. We're at 200 meters sea level change at the North Pole. We have a bit of a lower sea level change here, a bit higher sea level change here. So we've got a small raster which we can now use as an input. So now let's go back to raster processing and go to the calculator. And I'm going to choose GEBCO. And then I'm going to choose my sea level grid that I just created. And now I'm going to go A00 plus B00. So I'm going to add my sea level change onto my terrain and bathymetry. And this is going to lower the sea level. So we'll use that one. Hit OK. Come back in and just change my color table to Atlas. And here's the result. So you can see that again we've lowered sea level. We've lowered it by 300 meters at Antarctica, 200 meters at the North Pole, and if you recall from our little grid, we had a high over here near South America, so we've lowered the sea level more there, and over here near Japan, we didn't lower it quite so much. So now I'm going to raise sea level, so I'll go into the calculator. Again, just go through this quickly, select GEBCO, and then select my output raster, which was my sea level change. This is going to lower sea levels, higher sea levels, so I'll choose that. And I'm going to say GEBCO, which is A00, minus my change. Hit OK. Again, come in and choose that color table. And now we have raised sea levels, and Australia has turned into an archipelago. So just as a final visualization, we can swap between these products. So here's the sea level change that I created through my virtual gridding process, and just through a few input data points that I just pulled out of a hat and made up myself. Of course, you'll have your own analytically derived data points. So there's sea level raised, and there's sea level lowered. So in this case, we're adding on that change to the sea level, and in this case, we're subtracting that change from the sea level. And getting that effect on the GEBCO dataset. So I think I hope that shows you how you can model varying sea level change, or how you can apply a modeled variable sea level change to a dataset in ProRaster. Here I've been working with the whole globe, but you can work with any dataset of any size or any extent, and a similar rule or similar methodology will apply. Just use that virtual raster calculator capability. All very quick, does everything in real time, and you'll find it a very efficient way to work. Thanks for watching.